Okay, now we're going to solve that differential equation, the equation for exponential growth and or decay, depending on whether k is positive or negative. Step 1, we turn these into the Leibniz-style formulas. We say the derivative is df, df dt is k times f. Oh well. And then we separate it. We put all the t's on one side and all the f's on the other. K is a constant, remember? So we have df over f, when we divide both sides by f, is k times dt. Then we take the integral of both sides. The integral of df over f is the integral of k dt, whose derivative is 1 over f. Why? The natural log of the absolute value of f. Whose derivative is k? When you're taking the derivative with respect to t, it's kt plus c. What do? We take that. How do we get rid of that natural log? We get rid of that natural log by raising each side as an exponent of e. So e to the natural log of f, e to the natural log of the absolute value of f is the absolute value of f. And over here we just have e to the kt plus c. Well, e to the kt plus c is e to the kt times e to the c. We've done this sort of thing last set of videos. So f is plus or minus e to the c times e to the kt. And I'm not going to go through the whole thing again, but, and I forgot to mention this again, or your function f of t is just constantly 0, because in that case the derivative is 0, and that is k times a function that's continuously 0. So what do we get is f of t is a e to the kt. And this where a is a constant. And k is, what is it? It's sort of your growth rate, your proportionality constant. Well, k is a constant too. And that depends. In fact, we can go a little bit further. F of 0 is the amount at time t equals 0, and f of 0 is a times e to the k times 0, which is a times e to the 0, which is just a. So specifically, f of t is a e to the kt, where a is the amount at time 0, at time t equals 0. So that is to say that if you are talking about how is the population of a country growing from now, probably you're going to say t equals 0, the time 0 is now, and that the population, the initial population, the amount of population you have now is a. If you are talking about an amount of money growing exponentially over time, then we are going to say a is the amount of money you start with, the amount of money that you're going to have at time 0. If you're talking about radioactive decay, a is the amount that you start with at time 0. Oh, and this is called exponential growth and decay because it's an exponential function. The graph of y equals f of t, if you put it, here's the t-axis, here's the y-axis, it goes up like this. And this amount here is a, the amount at time 0, right? So you get 0a, that's how much you have. And, well, this is for if k is greater than 0, and this is why populations grow what we call exponentially. If k is less than 0, then what we have is exponential growth, exponential decay, where here is 0 and a, that is the point a, and it goes down. So if you are talking about the number of rabbits in a forest, and we're assuming that there's enough room for an unlimited number of rabbits, and there's enough food for these rabbits, do rabbits eat the kind of stuff in field? Let's put these rabbits in a field. If you have rabbits in a field, and you don't eat them or shoot them or do anything to make their lives difficult, the amount of rabbits you have are just going to go shooting up like this. Every year you're going to have more and more. You might start off with a few rabbits, they'll have a few babies, but after those babies grow up to maturity, now you have more rabbits, and more rabbits will have more babies, and so it will go up faster and faster and faster. If, on the other hand, you have some nuclear material, then you lose nuclear material, but then you have less nuclear material, and so less of it's going to go down. So it goes down less and less and less. We'll do some examples in a different video.